Hey guys, lesson 2, we're looking at logarithmic functions and their graphs today. So here we go. Log functions are inverses of exponential functions. We want to graph y equals a base to the x power and y equals a log base b of x and the identity function y equals x. So I'm going to get us started here with the graph of y equals x, because that's going to be on the diagonal right through the origin like such. So this is y equals x. And we'll make it a little thinner if we can do that. No, I don't know. Okay. Okay, so I made it thinner and turned it to red. Then the graph of y equals b to the x, we're going to do that in blue. Y equals b to the x would pass through the point 0, 1, no matter what the base was. The x-axis would be the horizontal asymptote, and this would be y equals b to some power x. And then the log base b would be a reflection across the line y equals x. That's this line, y equals x. We call that the identity function. And the logarithm graph would pass through the point 1, 0, because each xy on the exponential graph is flipped around on the logarithm graph, like such. So this is the graph of y equals log base b of x. So logarithms are inverses of each other. On this slide, you see the properties that we've seen since Algebra 2. Log base b of 1 is 0, log base b of b is 1, so on and so forth. So for common logs or logs of any base, and then for natural logs where the base is e. So you should be familiar with those properties. Whenever we have exponential form, say 2 cubed is 8, you can turn an exponential function into a log function by knowing that the log base b of a number is the power. Log base b of a number equals the power. Whoop. Where did that go? So in this case, the base is 2. The number is 8, so log base 2 of 8 is equal to 3 because 2 to the third is 8. In words, this property tells us that the base raised to some power is equal to a number if and only if, that means it's biconditional, it works both ways, if and only if the log base b of a number is equal to that particular power. So in this case, let's revisit that. Log base 2 of 8 is 3 because 2 to the third power is the number 8. Likewise here, log base 3 of the square root of 3 is a half because 3 to the 1/2 power is the square root of 3. See? Makes an E. 2 to the third is 8. 5 to the negative 2 is a 25th. 5 to the negative 2 is 1 over 5 to the positive 2, which is 1/25th. See how I'm using that little trick? If I make the letter E, I can see how the logarithm translates. 7 to the 1 is equal to 7, because 7 to the first power is equal to the number 7. And in this case, log base 6 of 11, that power, the base is 6, the number is 11, so the log for base 6 is 11 because 6 to the 11 is log base 6 of 11. So they all can be translated to a different statement. Now in this example, we're going to look at a table. That's the complete table. So on your notes, you have this particular table. And what we want to do is think about substituting -2 into the 2 to the x power, and we will end up with a completed table. Whoop, that's not it. Let's find that table. We'll end up with the completed table somewhere. No. So we'll end up with this completed table. 2 to the -2 is a fourth. So on the logarithm graph, the xy on the exponential graph has been switched around so that the y becomes x and the x becomes y. And your table should look like that when you're finished. Logarithms are inverses of exponential functions. Here we can evaluate logarithms and by using exponential expressions. I know that 10, if I thought log of 100 is some number, well, the base is 10, so 10 to some number has to equal 100, and 100 is 10 to the second power. So when the bases are the same, the exponents are equal, and I can evaluate in that really easy to follow format. On letter B, log base 10, again, my base is the common log, 10. So 10 to a power, 10 to some power, where's my pencil here? 10 to some power is equal to the square root of x, square root of 10, and square root is to the half power. So the number that I'm looking for is 1/2. Log base 10 of the square root of 10 is a number. Similarly, down here, we've got 10 to some power. We don't know the power. We're looking for that power. 10 to the power is 1/1,000. Well, 1/1,000 can be 10 to the third power. So 10 to the power, 10 to some power, is 10 to the -3. When the bases are the same, the exponents are equal. So the power, or the logarithm, log of 1/1000 is the -3 power. A logarithm is a power. And this one, the same thing. 6 to some power is 6. So that would be 6 to the first is 6 to the first. So that would equal 1. Here we need calculators, so I'm going to let you do that work, and you can check your work with mine. I get 1 and 0.538 for 3 decimal accuracy on log of 43 hundredths. I get 0.367, and then this one is not defined because we know that a logarithm is not defined for negative values of x. So if you thought about it, if you thought about this logarithm, think about the graph of a log. Here's the graph of log base 10, passes through 1, 0, and we're looking for a value over here at -3. So, doesn't work because you've got asymptotic behavior at the y-axis. So we could say something along the lines that a logarithm is not defined. Logarithms are not defined for negative values of x. Okay. In other words, the domain for a logarithmic function is from 0 to infinity. X can't be negative or 0, non-zero. Same thing again, if I have an equation this time to solve an exponential equation, we can change it to a log equation, and to solve a log equation, we can change it to an exponential equation. So I have a log equation, I know the base is 10, and I know 10 to the third power is going to be my number, so my number must be 1000. And in this case, I know that 2 to the 5th power is the number, because log base 2 of a number is 5, and a logarithm is a power. This is my power. A logarithm is a power. A logarithm is a power. So my number is 32. That's pretty easy. Remember, when your base is e, that's the same thing as natural log of x. So if we convert log base e of x, we can write that in the shorthand for natural log. And in this case, we want to evaluate the logarithm as e to some power is the square root of e. So e to that power has got to be the half power. The number, a logarithm, is a power, so the power is 1/2. This one is e to a power is e to the 5th, and the bases are the same. The exponents are equal. The power is 5. And then similarly, the natural log of x is the natural log of 4. So x is 4. We saw earlier that e to the natural log of a number is just the number, and that number is 4. So using the properties. Again, back to the calculator, we're going to practice with natural logs. Natural log of 23.5 is about 3.157. Natural log of 48/100 is about -734 behind the decimal. And what happens natural log of a negative number? That's not defined, undefined, doesn't exist, not possible. And then here's our properties. We know natural log of 1 is 0 because e to the 0 is 1. And so on and so forth. So we saw those earlier, but now we're going to use those properties to evaluate the natural logs. In this case, the base here is e, and we're looking for what power? So e to the power is e to the 7 when the power is 7. Here, this is e to the natural log is just the number. The number is 81. This is the same as this one, just different. So my answer is going to be square root of 9x, but we know the square root of 9 is 3. So we could say e to the natural log of radical 9x power is 3 times the square root of x. And in this case, if you rewrite natural log as e to the -5, then I know -5 is the result. And finally, we want to be able to analyze a natural log function. So similar to the log base b, we have a vertical asymptote at x equals 0. We have when natural log of 1 is 0, so we have 1, 0. And we're curving slowly, concave down toward the right. So we know the domain. We can say the domain is from 0 to infinity. The range is all reals from -infinity to infinity. Just like in chapter 1, we want to be able to thoroughly analyze. There's no symmetry on the graph. There's no maximum, no minimum. So we have no extrema. The graph is not bounded above or below. There's a vertical asymptote at x equals 0. We have an x-intercept at 1, 0. There's no y-intercept. We could say for in behavior, let's practice with our limit notation. As you approach 0 from the right, the function is unbounded downward. And as you approach positive infinity, the function is unbounded infinitely up. So we've analyzed completely. Then, now that we know the parent function, we want to be able to transform, and I've shown you here a slide of the graphs, but let's do each one of them individually. So if we have natural log of x plus 2, that's this green graph here, and that graph has moved us 2 units to the left over here. But at -2, we have a vertical asymptote at x equals -2. And when I say this graph is shifted 2 units to the left, what I really mean is that x-intercept, 1, 0, moves 1, 2 units to the left. It's now at -1, 0. That's my new x-intercept. And the graph goes off to the right like that. And that initial x-intercept, 1, 0, was shifted left 2 units with a vertical asymptote at -2. Now, in this case, h of x is reflected, and I'm going to rewrite it so you can see why. This is negative, and then I can flip around that argument, x minus 3. So this is going to reflect our graph over the y-axis. And the 3 is going to shift that point 1, 0, 3 units to the right, which is going to make x equals 3 our vertical asymptote. So the graph is reflected over the y-axis and shift that point, shift 3 units to the right. And let's take a look on our calculator. So the point 1, 0 was moved 1, 2, 3 units to the right, and the parent graph was reflected over the y-axis so that it's going off in the other direction. So our graph would be at 3, there's a vertical asymptote, x equals 3. At 2, 0, the graph has a x-intercept at 2, 0, 1, 2, 3, right? Okay. And then letter C, this is log base 10. So here, log base 10, the blue one is our parent. No, the blue one isn't. The red one is our parent graph. And this one, 3, we've got a stretch factor of 3. So we're going to be vertically stretched. It's going to grow much faster than the parent graph. The parent graph's red, and you can see the green graph is growing much quicker. It's still going to have a vertical asymptote at 0, and 1, 0 is our x-intercept, but 10, 3 is our y-intercept, is our another point that's growing much quicker. We go way out and 3 up, okay? This log of 10 is 1, and 3 times 1 is 3. And then finally, our last one, we have a +1, so this is moving us up 1 unit from the parent graph. Let's go look at that. So the parent graph 1, 0 is going to move up here 1 unit. So this point will be 1, 1 in our graph. That's the effect of this. And x equals 0 is still our vertical asymptote, just like it was over here. So we have the same thing going on here, x equals 0. And instead of the point 1, 1 being our x-intercept, we've taken that point 1, 1 and 1, 0 and shifted it up 1 unit to 1, 1. So your x-intercept is some decimal value in here. I didn't take the time to figure that out. Okay, so that's a pretty quick lesson, and I'll see you next time. We'll talk about properties of logarithms.